Welcome everybody to our tutorial on knowledge graph embeddings for natural language processing from theory to practice. I have a pleasure to introduce my colleagues. We will have today Luca Costabello, Sumit Pei, Eda Bayram, and myself, Adriana Janik. We are a team from Accenture Labs, and I wish you a pleasant tutorial. If you would like to refer to these materials any time in the future, or would you like to ask some further questions, you can reach out through our tutorial website, where you can find the URL in the top right corner of this slide, KGE4NLP COLING22.github.io. And please reach out and enjoy your tutorial. Thank you. Before we immerse ourselves in the world of knowledge graph embeddings, I would like to briefly tell you about what we will be talking about today. We will start from foundations, and we will have introduction, anatomy of knowledge graph embedding model, and evaluation protocol and metrics, which will be presented for you by Luca Costabello. Then we will switch to advanced knowledge graph embedding topics by myself, and we will also touch a bit on some open research questions. Then we'll switch to Eda Bayram for knowledge graph embeddings for natural language processing section. Then we'll have a break and a QA session for the ones that are live in person in Gwangju. And then we will switch to application and software ecosystem, again by myself. And at the last but not least, we will switch to Sumit Pei for exciting hands-on session. So once again, have a great tutorial.
Thank you for the introduction, Adriana. My name is Luca, and in the next 40 minutes or so, I'll give you an overview of the foundations of knowledge graph embedding models. I will start with an introduction just to set the scene, and then I'll move straight into how these methods work under the hood, and then I'll conclude with an overview of the evaluation protocol and the metrics that are adopted in the literature. Now, what is a knowledge graph? A knowledge graph is a knowledge base represented as a network. It's made of nodes and edges. Nodes are connected with binary relations, so a pair of nodes are connected together, and the connections are labeled by human readable strings, so we're talking about labeled edges. Edges are directed, so there is always a subject and an object of a statement. And it's also important to point out that nodes are connected with multiple relation types, so nothing prevents you from adding multiple link types between two nodes, like in the picture here. Now, the set of triples or statements that we see in the picture here make a knowledge graph, right? And there is a great introduction to knowledge graph in this paper by Aidan Hogan and others published a couple of years back, which I really invite you to read if you're interested in additional details. Now, just to give you a sense of the of what is out there, of the size of these knowledge graphs, I put on the slide here 3 examples of publicly available graphs. One is Yago, another is Wikidata, and then we have DBpedia. Very popular and well-known knowledge graphs which have been around for a good few years now. You see here on the slide that they're really big. They include hundreds of millions of statements, even billions of them, and they include dozens of nodes, and so we're talking about graphs which are really large, and they include a lot of heterogeneous information. So when we talk about machine learning on knowledge graphs, it's important to get a first understanding of the kind of tasks that we can carry out on top of these data structures. Well, first thing first, we need to keep in mind that probably the first class citizen of machine learning tasks here is link prediction, also known as triple classification. And this is the task of predicting whether there is a missing link between two nodes in a graph. Now, this can be used for many different use cases, from knowledge graph completion to content recommendation to knowledge discovery in general. But machine learning on graphs, it doesn't really stop there. It goes beyond that. We can use these techniques for collective node classification, also known as link-based clustering. So pretend you're working in a customer segmentation use case, and you can leverage a knowledge graph to group similar customers together, right? Like in the picture here. Or we can use graph machine learning for entity matching to duplicate entities, nodes of a graph, and this is something quite interesting because it leverages the network of a graph, the connection of the graphs to come up with solutions to the problem. Like in this case here, we have A.Guinness. Is this Arthur or Alec? Well, we can take a look at the topology of a graph and conclude that we're talking about Alec and not about Arthur. If we drill down link prediction, which I said a minute ago is the first class citizen here in today's tutorial, we can take a closer look at how this task is considered and described in the community. So there are fundamentally two ways to address the problem. One is by going down the road of link prediction, so casting the problem as a learning to rank task from an information retrieval point, and you'll see details later on with me in this tutorial. Again, it's worth pointing out that when we talk about link prediction, we have no ground truth negatives in the test set, so they're not required, and you'll see in a minute why. Whereas if we speak about triple classification, this is a slightly different flavor of the same kind of problem, predicting two links between nodes, but the way we cast the problem is a bit different. So it's a binary classification task with binary classification metrics, and we need both positive and negative ground truth statements, right? And to give you extra insights on link prediction, we should also point out that there are two flavors of link prediction, one being transductive link prediction, which is the task of predicting a missing link between two nodes in a graph, like in the picture here. So there's no based-in link between Acme and Liverpool. The link prediction task is assigning a, for example, probability estimate that that link is factually correct. This is transductive link prediction. The two nodes are present in the training set from the start. They occur in the training knowledge graph. But there is another flavor of link prediction though, which is known as inductive link prediction. Now, this is when either the subject or the object of the link that we want to predict do not occur in the training knowledge graph. Like in the picture on the screen, pretend that there are a couple of triples, like Mohamed Salah is a person and Mohamed Salah lives in Liverpool, that do not occur in the training knowledge graph. So the model has never seen them, therefore it has never learned a representation for them. We'll see how that works in a couple of minutes. Now, if this is so, the model will be unable to predict the place for link between Mohamed Salah and Liverpool Football Club. So keep in mind there are these two flavors of link prediction. So entering the world of graph representation learning, which boils down to learning representations of nodes and edges of a graph. So turning a graph from the realm of nodes and edges into internal representations, vectors of floating point numbers, which can have k elements, where k is usually something between 100 and say 500, so quite compact representations. And once we have that, we can use these vectors for downstream tasks, such as link prediction, for example. Now, graph representation learning went through a good few phases. The early works started off by looking at ways to represent nodes by using graph feature-based methods like random walks. The PRA and line methods are good examples of this family of methods. Then we have the fast-growing area of graph neural networks, and I'm sure some of you guys must be familiar with the topic. So graph convolutional networks, graph attention networks, graph search, and so forth. And then we have a family of methods which were born pretty much in the same time with graph neural networks. We're talking about pretty much the same years, which are called knowledge graph embedding models, knowledge graph embeddings, KGE in short. And this is the scope of the tutorial. These are neural architectures, artificial neural architectures, which are quite similar to graph neural networks, even though there are some differences. And this is the scope of the tutorial, where today we will discuss our methods. So what is a knowledge graph embedding model then, a KGE model? Well, it is an artificial neural network designed to automatically learn embeddings, which are nothing than projections of nodes and edges into, like I said a minute ago, a continuous low dimensional space that include typically a few hundreds of parameters for each node or edge type that we learn. We will see together that the knowledge graph embedding models that have received the most attention in the community are designed to capture a number of knowledge graph patterns and regularities, which are really typical of these data representation paradigm. And so we need to keep in mind that this is how the data looks like, so our methods must make sure that capture this information. So for example, we may have triples that are symmetric, like Alice married to Bob, or which are not symmetric, like Alice child of Jack. It's obviously not a symmetric piece of information. We can have inversion as well, so we can invert the triple above by adding Jack father of Alice, or we can have composite relations like Alice child of Jack, but Jack sibling of Mary, and so we can have another triple which is Alice niece of Mary. So this is quite common it is quite common to find these patterns in knowledge graphs, but there's more. There are hierarchies, all kind of type constraints. There are transitive relations, homophily. So knowledge graphs are known to have quite a lot of homophily, so similar items, nodes, and in general entities that have something to do together. They usually occur in the same neighborhood of the graph, but there are also long-range dependencies. So there is sometimes there are effects of multi-hop triples between nodes in a knowledge graph. So all this must be kept into account when designing machine learning methods. To give you a rough understanding of where we are with literature, I put the most significant works on a timeline. And so you'll see that we started a few years back with a model called Rascal, and then we moved all the way down to a few months back when this method has been published in literature. So we have a couple of important methods that are quite well adopted, not only in academia but also in industry, and we'll see how they work in a minute. Now it's interesting to point out that the design choices of these methods usually try to make sure that each of them captures the regularities, the patterns that I described in a couple of slides back, because the goal is obviously to maximize predictive power, and therefore these methods must be designed to capture all these patterns in the data. Now, I have introduced what knowledge graph embeddings are. Now, what I would like to do in the next section is talking a bit about the anatomy of these methods, describe how they work under the hood. Just in general, what you see on the screen here is the architecture of a conventional knowledge graph embedding model. It's like I said before, a method based on artificial neural networks. It takes a training knowledge graph as input on the left hand side, and then it processes such graph in a supervised learning manner to generate embeddings of nodes and edge types, which will be used later on in downstream tasks. And this is what happens at inference time. In the next few minutes, we will go component by component in that block diagram, and we will see how these components interact with each other and what is their design rationale. We start from the so-called scoring function f, which is a very important component of a knowledge graph embedding model. Now, what is a scoring function? It is a function, an equation that assigns a score to a triple SPO. Now, high scores means that the triple is very likely to be factually correct, right? So this is the rationale behind a scoring function. High score means triple is factually correct. Most of the conventional knowledge graph embedding models differ from the kind of, I'm oversimplifying here, but they differ from the kind of scoring function, the scoring layer that they adopt. And I will now give you a quick overview of some of the most popular methods, starting from a family of scoring functions which are known to be translation based. And I will start from the forerunner of these methods, translating embeddings, TransE, which is a paper from 2013. This is a fairly famous knowledge graph embedding model that works as follows. Now, the method includes the scoring function that I described here, and it is fundamentally a computation of a distance. It could be Euclidean distance or another kind of norm, but in general Euclidean distance is adopted, and it works like this. Now the translating embeddings function computes the embedding of, takes the embedding of the subject ES, it adds the embedding of the predicate RP, and it reaches a specific position in the knowledge space. And then it compares the embedding of the object EO, right, which let's pretend it's in this position, and then it computes the distance between these two embeddings. Now the rationale is that the closer the distance, the higher the chances that the triple is true, because it means that if the subject plus the predicate type makes you go into a very close area in the embedding space as the embedding of the object, it means that probably that triple is factually correct. So this is how the scoring function of translating embedding works, the rationale of it. And this idea has been used by other models, one of them being rotate, but instead of using translations, adopts rotations instead, and it comes up with a pretty original approach to the problem. And by the way, it operates in the realm of complex numbers. We'll see in a minute why. And again, there are a lot of other translating based methods, but they're not included in the tutorial. We'll advise to look up literature to get a better understanding of what is the landscape. There are a lot of methods that instead of being based on translations, they are grounded on factorization approaches. The first one and most famous is probably Rascal, that was proposed in 2011. It consists in a low-rank factorization procedure that uses tensor products to factorize the adjacency tensor of the triples in a knowledge graph. There is then another factorization based technique called DISMOLD, which is a pretty popular model as well. It's a bilinear diagonal model that leverages dot product. It's a pretty simple scoring function, but very effective. Model proposed in 2015. And there is an evolution of DISMOLD, which is the real workhorse of knowledge graph embeddings, which is called complex. Complex being an extension of DISMOLD in the realm of complex numbers. Now, why complex numbers? DISMOLD, while being effective, however, it has a problem, a shortcoming, which is rooted in the dot product itself, dot product being symmetric, whereas, as you can remember from the early slides, a lot of triples in the knowledge graphs are asymmetric. So the goal of the authors of Complex was to come up with a model that had a asymmetric scoring function to better model the asymmetry relations in the knowledge graph. And the authors came up with the intuition that the dot product in the complex space is not symmetric, and the complex model leverages that intuition. It's worth pointing out that there are other methods with deeper scoring functions, one of them being convolutional embeddings that uses convolutions on 2D representations of the triples in the knowledge graph. There is also an extension of conv called convkb that uses a combination of convolutions and dot product. Now, the problem with these deeper methods is that they are computationally expensive, so training them takes way longer than the methods that I described earlier on. There is another bunch of models. Again, the knowledge graph embeddings literature is quite rich. I've put some of them on the slide here. You can take a look, and again, Some of them are built on slightly different intuitions, but the goal is always to come up with scoring functions that assign high scores to triples that are likely to be correct and low scores to triples which are not factually true. I'd like to say a few words now on the loss function, which is another important component of a knowledge graph embedding model architecture. Now, there are a lot of different loss functions adopted in the literature. I'd like to spend a bit more time on the pairwise margin-based hinge loss, which is the equation that you see on the screen, because this is probably the most intuitive loss function in the area. So I will briefly give you an understanding of how it works. This is a function that makes you pay a penalty if the score of a positive triple, T plus, is lesser than the score of a synthetic negative by at least a margin gamma. Now, we haven't said a word about synthetic negatives. We will touch upon that negative generation component in a couple of slides, but pretend there are a bunch of negative triples, facts which are not factually correct, which are negatives, and they are associated to and merged with facts from our knowledge graph, positive statements, factual knowledge from the training set. Now, we process triple by triple in this nested loop. So we process every positive in the knowledge graph, every triple in the knowledge graph, and for each triple in the knowledge graph, we iterate over a number of synthetic negatives generated from it. And for each of them, we assign a score using the scoring function of the model, a score assigned to the negative triple and a score assigned to the positive example. Now, these theta parameters are the embeddings we optimize for. And then we compute the maximum between 0 and the subtraction between these two scores, plus factoring in a margin gamma. So the goal is that if the difference between these two scores is greater than gamma, then we don't pay a penalty, otherwise we do. And the optimization procedure that we carried out with stochastic gradient descent optimizes for this objective. Now, like I said, this is one form. There are multiple ways to encode that intuition in using other losses. We can use negative likelihood, like in the equation below, where this is the label of the triple being processed. So it could be positive or negative. In this case, we process the union of the knowledge graph G and the set of corruptions created for the triples in the knowledge graph. Again, this is yet another form of loss function, but there are many more. Like, we can use binary cross entropy, or we can adopt something proposed in the Rotate paper in 2019. It's called self-adversarial loss, where we consider as well the weight for the negative sample in the mix. But again, without going into fine-grained details, it's suffice to say that there are many more loss functions out there, like multi-class negative log likelihood, absolute margin, and so on. So this is a rich area, and the combination of scoring functions and loss functions is probably what determines the greatest differences between papers in this domain. It's worth mentioning that these architectures benefit from regularization, just like traditional conventional artificial neural networks. You can apply L1 or L2 regularizers, or you can adopt the L3 regularizer proposed by Lacroix and others in 2018 in the complex N3 paper. Some architectures have adopted dropout, like convolutional embeddings. Again, this is an area which there are a lot of variations on the theme. Initializers, well, usually we'll find different ways to initialize these embeddings, but again, there's nothing too weird or specific. Again, random initializations or Xavier initializers will do, and are pretty popular indeed. Where things are a bit different from traditional neural architectures is the way we generate negative examples. I said a couple of times so far that we train knowledge graph embedding models in a supervised manner, so we need positive and negative examples. So you may ask yourself, where do all the negative examples come from, right? Or where do these false facts come from? Knowledge graphs don't include false facts. Well, we make them up. We generate on the fly, exploiting the so-called local closed world assumption, which states that the knowledge graph is only locally complete, right? So if you look at a very specific area of a knowledge graph, then we can consider it as complete. So we are more inclined to corrupt it, to swap, replace subjects and objects of triples with other nodes of the graph to generate statements that don't make sense, right? And this is exactly what we do. We create corrupted versions of triples, and we use them as synthetic negatives. So we define the set C of corrupted triples that include a corrupted subject S hat, and or triples with a corrupted object O hat. Now note that the predicate is always unaltered. We never change it. We either change the object or the subject. It's probably clearer if we go through an example together. So if these are the nodes of the graph and these are the relation types, and we take a target triple Mike born in Liverpool and we want to generate a set of corruptions for that triple, we can go about by replacing either the object, like in this case, or we can replace the subject, like in these two triples at the bottom. In both cases, we come up with synthetic negatives or corruptions that we will use during training. There are a few different strategies to come up with these negatives. One is to generate all possible synthetic negatives and then sample n negatives for each positive triple T. That's by applying uniform sampling, or we can use the complete set of corruptions, so no sampling at all. Use all the possible synthetic negatives for each positive triple in the training set, but be careful because this may lead to quite a large training set, right? And so this will hamper the training time, and it's not necessarily a great benefit to predictive power, so one has to strike a bit of a trade-off between the number of synthetic negatives that are generated during training. There are some works that adopt the so-called one-to-n scoring strategy, so they split the training set in batches of couples, and they create all possible combinations on the fly, and they label them as positives or negatives according to the fact of whether these triples created on the fly are included in the training knowledge graph or not. No, it's another variation on the theme, but the take-home message is that we create these synthetic negatives to make sure that we have these examples to train the model and learn how to tell true facts from false facts. How does the training procedure work? So we optimize using stochastic gradient descent, and we use some of the stochastic gradient descent variance to minimize the loss function that we presented a few slides ago. This leads to optimal parameters, the embeddings, and that is done again by conventional backpropagation. Now, it's worth pointing out that some works inject reciprocal triples in the training set. So an example of reciprocal triple is shown here on the slide. And so this is important when comparing methods and to make sure that comparisons are done in the fairest way. A word on hyperparameter selection. Now, when it comes to select the best combination of values for hyperparameters, we can adopt conventional methodologies like grid search or random search, or fancier methods like Bayesian approaches. Again, there are a few proposals out there in the literature. And with that, I will now move on to explaining how to evaluate these methods. Just a quick refresher on the task at hand. We are predicting missing links, and we cast that problem as a learning to rank task using information retrieval metrics because we don't have ground truth negatives. So by all means, we are trying to figure out how well positive triples in a test set are ranked against their synthetic negatives, against their corruptions. So this should ring a bell. This is exactly the same procedure we have described a few minutes ago when training the model. So we reuse the same procedure, but this time to evaluate how well the method performs on a test set, right? And to give you an understanding of what these metrics are, I'll give you a quick overview of the most popular. We will use the mean rank of the triples. Rank again computed against, for each triple, against a set of synthetic negatives. This metric is a bit too sensitive to outliers, so in practice what is being used is a variation of this metric called mean reciprocal rank, where we simply invert the rank so that high ranked triples which have not been learned properly by the model do not mess up the score entirely, so it's a bit less sensitive to outliers. And then we have a metric called hits at n, which is in short how many times our test triples occur in the, say, top 10, top 3, top 5 rank against, again, a set of corruptions generated on the fly. Again, like for the examples I shown before, it's probably simpler if we look at this simple example together. So the task is to figure out how well the positive triples in a test set are ranked against their synthetic negatives. Now, the test set is made of two triples, Mike, friend with George, and Mike, born in Liverpool. We process each of them separately, and for each of them we generate 4 negatives. Now, in this case, so where the positive is Mike, friend with George, the model assigned a score which is the highest of the group. So the true positive is ranked first. This is the optimal outcome because the model can tell the true fact from all the other corrupted versions of such fact. So Mike, friend with Jim is a false fact. Acme, friend with George is also obviously a false fact. Mike, friend with Liverpool, same. And these statements are all assigned a lower score, and therefore this is the optimal solution. Now in the second example though, the positive triple is Mike, born in Liverpool. Unfortunately, the machine learning model assigns a higher score to Mike, born in Leeds. So the rank of the positive is 2, It's not the best outcome, but it's still pretty good, right? And by taking into account these two ranks, we can compute these aggregate metrics. So the mean rank is 1 plus 2 divided by 2, so it means 1.5, or saying we can compute the MRR, the mean reciprocal rank, or how many times the positive has scored on top, hits at 1, so once out of 2 cases, so 0.5, or how many times the positive occurred in the top 3 elements, which is 100% of times in this example. So this is how these metrics work. And so how can we use these metrics on community-defined benchmark datasets? Now, first let's take a look together at what are the benchmark datasets out there. The most used ones are the ones in the list here, and they are all split of popular knowledge graphs available online. The community is competing to achieve the best results, and again you'll see that the metrics that are reported in papers are the ones I've presented earlier on. So competition is quite tight, and a lot of works seem to bring similar results on the table. Now, I'd like to point out a couple of aspects about comparing results. It's worth pointing out that comparing results is tricky, and you should be aware of a number of aspects that play a role in that. For example, what kind of training strategies are being adopted, or whether reciprocal relations have been injected in the training set, or whether you're dealing with an unfair or suboptimal model selection, or even what happens during the evaluation protocol. So is it fair? What's the behavior with tie ranks? And also what happens if we replace the loss with another loss? Can we run ablation studies? What's the effect on the overall system? So all these aspects are quite important and should be always taking into account. And with that, I conclude, and I will hand over to Adriana that will tell you all about advanced topics on knowledge graph embedding models. Thank you.
Thank you, Luca, for presenting foundations of knowledge graph embeddings. Now I would like to switch to more advanced topics and research directions that are being explored. We will talk about multimodality, uncertainty, time, explainability, robustness, memory, reasoning, and we'll conclude with open research questions. Now let's talk about multimodality and support for heterogeneous data in knowledge graph embeddings. Many real-world graphs include multimodal attributes, like in this example on the slide. We have a subgraph representing Dublin City, which is many attributes. Some of them are simple, some of them are more complex, represented by different modalities like images, dates, or description, textual format. To make things more complicated, nodes and edges can also have properties, like in this example. The same information that could be represented as separate nodes and edges can be represented as properties of a single node. This would be equivalent to such representation. Dublin, with its latitude and longitude, represented separate nodes, and also type. This could be also included in one node. These features could be also missing, and this is a separate branch of research when this kind of data structures are also looked at. This type of data is called property graphs, and we will focus on multimodal graphs without properties on the nodes. So how to deal with such modality, such plurality of modality. One example is to use modality-specific encoders to embed objects, and some other works use deep learning to deal with multimodality and temporal aspects. Another very important aspect of real-world knowledge graphs is time. Many of them represent time-stamped concepts, and you can see that in the example on the slide. We have a fictional patient, Tia Morris, who was admitted to St. Vincent's University Hospital in Dublin. And it happened on 28th of March 2022. This is a time-stamped edge. We can see there are many more edges that are time-stamped. For example, born in, representing the edge with the date of birth, which happened on 1992, 18th of February. Also, the time of diagnosis by Dr. Keira Mills. And when her friend Kian Rees visited her in the hospital, 29 March. These are events that are important in real-world graphs, but are not trivial to represent in the knowledge graph embeddings world. There is a continuous line of research in this direction, and many papers have been published since in the last few years, starting from T-Transi in 2016, through TA-Dismult, Conti, D-Simply, TNT-Complex, Chrono-R, and Box-TE, which were published recently. This is by no means an exhaustive list, and the field is growing very quickly. So this is just to give you an overview of what temporal aspect of knowledge graphs is. Another important subject which grows in popularity in recent years in machine learning and deep learning is explainability. But before we jump straight into explainability for knowledge graph embeddings, let's look a little bit at interpreting and at understanding predictions. Predictions from trained knowledge graph embeddings are hard to interpret on its own, and we use something called calibration to allow for estimation of output probabilities. This is done by introducing an extra component called calibration, and it helps us provide calibrated probabilities, which is more interpretable on its own. Now let's move on to explainability. One of the recent works from last year is gradient rollback, which estimates influence of triples for the given prediction. We can see that target triple Volunteer Park, located in USA, has the most influential triple highlighted in green and red. And this is what most work that look at this direction do. They try to identify most influential triples and return them in a ranked order. From explainability, we can switch towards adversarial attacks and robustness. Because as it turns out, identifying most influential triples and deleting them can provide an interesting adversarial attack strategy. This work was explored by Bardwai and all. From this step, we can go back to explanations, and we can play between adversarial attacks and adversarial explanations. This was explored by Betts et al., where they identified regularities in the knowledge graph and based on this knowledge they design their attacks. How to make the knowledge graph embeddings robust against them? That's an open problem. Memory efficiency is something that knowledge graph embeddings can suffer from, because all the models that we previously seen, or most of the models that we previously seen in the foundation part, they require embedding for each unique entity and relation. So this requires a lot of memory, so it's a big matrix, and it can grow bigger with bigger dataset. However, recent work by COLING et al. Introduced a work named NodePiece, where they propose an approach where they are able to train similarly good models with 10 times less parameters by learning a target node embedding by passing a hash sequence of top k closest nodes, relations and distances to target to an encoder. 10 times, up to 10 times smaller. That's quite a increase in memory efficiency, don't you think? Another interesting direction of research is neurosymbolic integration, or as others call it, neurosymbolic approach, and it's appearing across many different machine learning and deep learning and artificial intelligence subjects. So the question is here, how do we integrate symbolic reasoning and neural reasoning into one framework which can solve precisely problems and in an approximate way with, for example, gradient-based algorithms. One such work is a background knowledge injection with soft constraints. This work provides an approach to manually provide rules and inject them into a loss function. Another work from the same line of works is work on neural theorem provers with blends of knowledge graph embeddings and rule-based models, and they can take the best of two worlds, so good generalization power, scalability from knowledge graph embeddings, and interpretability of rule-based approach. NTP implement reasoning in fully differentiable architectures, and symbols are replaced with embeddings. We can see example here from Rock-Teschel et al. Another interesting work from a different reasoning regime, analogical reasoning, is a work called Analogy, which allows to explicitly model analogical structures in multi-relational embeddings. So, for example, in this slide we can see that nucleus to electrons is as sun is to planets, and mass to planets is similar to charge to electrons, which is represented in a parallelogram, which could be represented in a parallelogram, and this is explored in this work. And this is a differentiable analogical reasoning combined with knowledge graph embedding models, which is also interesting. Let's conclude with some open research questions that are currently under exploration by the research community. Firstly, more expressive models. Model knowledge graph regularities and dependencies while keeping runtime and space complexity low. So we've seen example of node piece, but this is just the beginning. Let's see what will future provide. Another aspect is support for multimodality, and node and edges attributes time awareness, and they are still in their infancy. Robustness and interpretability. So how to dissect and investigate, explain, and protect from adversarial attacks. And finally, going beyond simple link prediction. How do we make predictions on multipaths? And how to adopt that in larger differentiable architectures to inject background knowledge from graphs. These are all questions, but there are many more. So now we will switch to Eda, who will present knowledge graph embeddings for NLP. And that's all from me from now. And thank you. Here's relevant literature that I mentioned during previous slide. You can explore it further.
Hello everyone, my name is Eda Bayram and I will take over the tutorial for the next 20 minutes in order to present a survey on the studies at the intersection of knowledge graph reasoning and NLP. I would like to first have a look at the problem of mapping a natural language text to a knowledge graph. Here, the main challenge is the semantic gap between the natural language text and knowledge graph entities and relations, which is also called as semantic loss or the lexical gap. The semantic gap may occur due to relationships having various expressions in natural language text or the ambiguity in the named entities. That emerges the following subproblems in the alignment of the text and knowledge graph. First, named entity recognition targets extraction and tagging word tokens into predefined semantic types such as person, location, organization, etc. Second, entity and relationship linking aims identifying entities and relations mentioned in the natural language text, linking them to corresponding ones in the knowledge graph. Then, schema linking relates to the alignment between natural language and the knowledge graph schema. Another common NLP problem is natural language question answering. In particular, question answering over knowledge graphs aims at finding the set of entities and relations in the KG which constitutes the answer to a given question in natural language. The predominant approach in question answering over knowledge graphs is semantic parsing, which is mapping of the natural language question onto logical form. When questions and answers are expressed in natural language, however, it is not straightforward to map them to strict logical queries because of the semantic gap issue mentioned earlier. A common technique is to represent the natural language question in a structured form with a semantic graph or the query graph, and then evaluating the answer entities on that representation. In order to be complete, I would like to also mention the line of works which does not deal directly with natural language question, yet assumes the question is readily given in the first order logic form. That involves logic operations such as existential quantifier, conjunction, disjunction, negation. For instance, the question, where did Canadian citizens with Turing Award graduate, can be represented as a first-order logic query, as showed in the figure. I would like to give an example from a couple of recent solutions addressing complex logical query answering, which also wrap the task of knowledge graph completion with it, aka the prediction of missing links. To start with, the query-to-box logical reasoning framework learns embedding of the KGE entities in a vector space where they represent the queries as boxes. They achieve this by learning parameterized logical operators over boxes by training on a set of queries together with their answers. Next, the framework continuous query decomposition has a compositional learning scheme where a pre-trained knowledge graph embedding is used in an optimization problem with logic operators formulating the complex query, which is done by a beam search. Although such a search is exhaustive, the compositional pipeline frees complex query decomposition from training on the complex query and answer set. So it is trained on simple queries, and this gives the capability of out-of-distribution generalization on complex queries. Moreover, it provides explainability for the answer to the complex query by digging the intermediate answers to the subqueries composing the complex query. Now, let's go back to the natural language line again and continue along the line of KGE representation learning. I would like to refer to several studies which aims at enhancing the knowledge graph question answering framework through knowledge graph embedding learning. The first one is knowledge graph embedding based question answering by Huang et al. In this work, given a simple natural language question that can be mapped by one triple fact in a KGE, the framework learns head entity and predicate representations. They achieve this by performing a joint search of representations both at the KGE embedding space and the entity and the predicate embedding space that they learn from the natural language questions. Finally, scoring function of the KGE embedding model is used to predict the tail entity embedding, which is mapped to the closest triple fact in the KGE, since this method does not involve prediction of missing facts. On the other hand, another framework called Embed KGE performs multitask learning where natural language question answering and knowledge graph completion take place together. It learns the embedding of natural language question and relation matching using the model Roberta. Then entity embeddings are learned via the KGE embedding model complex. Finally, the question embedding and the anchor node embedding are combined together to predict the answer. Thus, Embed KGE has the capability of answering complex questions requiring multi-hop queries on the knowledge graph. Following along the lines of KGE completion task, there are also studies enriching KGE embedding with pre-trained language models. By fine-tuning the language model using the textual description of the entities and relations. For instance, KGBERT treats knowledge graph triples as textual sequences and performs link prediction with a new scoring function. Since they train language model with the text corpus, they can generalize the representation to the entities that are unseen in the training knowledge graph. However, they do not directly deal with natural language question answering. Another framework called Kepler performs multiple tasks. Several NLP tasks such as relation classification, entity typing, and also link prediction in both transductive and inductive settings. They achieve this by jointly optimizing a pre-trained language model with textual descriptions of entities and knowledge graph embedding model. Kepler is able to produce embeddings of unseen entities during training from their text descriptions. Entity embeddings are encoded via transformer architecture from their text descriptions. Then, knowledge graph embedding is trained with the objective of the model rotate E. Previously, we have covered the marriage of pre-trained language models with knowledge graph embeddings for knowledge graph completion task. Now, let's have a look at why we may need to augment language model with knowledge graphs for NLP tasks. As you know, large pre-trained language models have become the dominant paradigm in many NLP tasks. Pre-training on unstructured text corpora, they learn to implicitly encode broad world knowledge and fine-tuning for downstream tasks. Yet, they have lack of explicit structured knowledge, hence they may not realize structured reasoning. On the other hand, knowledge-intensive NLP tasks motivates knowledge graph augmented language models, since they are highly rely on the external knowledge sources, explicitly storing the relationships between entities. Such structured knowledge can be integrated either in the pre-training stage or in the fine-tuning stage, or in an hybrid way, depending on the task and the external knowledge source. The post-fusion methods, in particular, first capture the relevant knowledge from the KGE and then perform joint reasoning over both the language context and the knowledge graph. On one side, language models have broad coverage, but they have the lack of structured knowledge. On the other side, knowledge graphs has the lack of coverage, but they provide structured word knowledge. Yet, how to reason effectively with both sources emerges the following sub-problems. First, how to identify the fragment of knowledge in the knowledge graph relevant to the given language context. Second, how to perform the joint reasoning over both on the language context and designated knowledge graph entities. Here, I would like to exemplify such a joint reasoning approach by a study addressing natural language question answering. KGE4NLP by Yasunaga et al. Unifies the question answering context and the relevant subgraph from KGE into a new graph representation. The QA context is encoded by the language model. First, it retrieves a subgraph of the knowledge graph, then it realizes a relevancy scoring of the KGE entities conditioned on the QA context using the pre-trained language model. This solves the first sub-problem. Next, the joint reasoning problem is solved with a graph neural network model, which updates the graph representation with a message passing mechanism that is aware of the entity and relation types, and with an attention mechanism that is additionally aware of the relevancy scores. Finally, the answer is inferred by calculating the probability over question and answer choice pairs. Later on, this approach is extended by a method called GREASE-LM, which jointly updates the textual representation with the graph representation through layers of their model, which mixes the representations through a modality interaction layer. Finally, I would like to briefly mention several conversational AI studies which enjoys the structured factual knowledge brought by KGEs. First of all, we can say that OpenDial KGE promoted the research on KGE-based conversational AI systems by publishing a large-scale conversational dataset with a rich underlying knowledge graph. Later on, Attention.io adopted the idea of attention flow with a graph neural network-based neighborhood aggregation for dialogue-conditioned path retrieval problem. Finally, Neural Path Hunter addressed reducing hallucinations such as generated incorrect statements with knowledge graph supervision. With this, I complete the part covering knowledge graphs for natural language processing. And here are the references used in this section. Thanks for listening and enjoy the rest of the tutorial.
Hello again. On this section, I will talk a little bit about applications and available software ecosystem. Let's get started. Some industrial applications that we have worked on in the team include pharmaceutical industry and predicting drug side effects. Also oncology, lung cancer patients' relapse prediction, and consumer products with customer segmentation. First, we will look at drug development. From gene identification and defining a compound to target the gene and experimentation on animals and humans, it is a very convoluted process. Some of the steps include target identification, target validation, preclinical trials, human clinical trials, and finally regulatory approvals and manufacturing. The whole process can take between 7 to 10 years, and it's time-consuming and very expensive. The single step of identification of gene drug takes several years, and if not identified correctly, may result in loss of money and time. So-called drug developers identify genes drugs by reading the latest research before proceeding with experimentation. But this is highly dependent on the experience of the person. The idea here is that we can use knowledge graph embeddings to recommend potential targets in a shorter time with a better outcome. Here is just an overview, a subgraph, how such data could look like in pharmaceutical industry use case. For example, in drug discovery, drugs side effect prediction, or determining risk factors. So we can see a lot of genes, variations, drugs, phenotypes, and how these nodes are connected with each other. And we can pick any edge that we could like to predict and see how plausible that would be with knowledge graph embeddings. In another project on the oncology side, we look at lung cancer patients and we try to predict whether they will relapse in the future or not. For this, we model patient data into a graph, and we try to predict his relapse prediction link. We also wanted to ask the question, why? So how do we explain such prediction? What does it mean that patient 9714186 has probability of 72% of experiencing progression relapse? Like, what is behind this number? We explain this prediction by providing other past examples that of patients that also relapse in the past. So we created this kind of reports for each patient that this is an example. This patient will relapse with 72% of chance, and as an evidence for that, we bring to your attention one similar patient that also relapsed. and we list also features that are in common between these two patients. For example, diagnosis, tumor histology, stage group, M stage, diagnosis stage, cancer type, and also some differences between the patients. In another project, we looked at customer segmentations and especially beer customers' marketing segmentation. Here, similarly as in drug discovery projects, traditional customer segmentation is expensive, time-consuming, and requires manual label dataset, which is difficult to acquire. And also qualitative surveys fail to consider consumption behavior. We ask a question like, how can we learn meaningful customer segments by only processing behavioral consumption sequences without human labeling and with no demographics or consumer survey information? A hypothesis that we pose was sequences of consumed beers hold enough information to tell customers apart. And as a solution, we provided unsupervised customer segmentation with graph and knowledge graph embedding. And what we noticed is that we did learn meaningful clusters without the need of customer surveys or expensive data annotation campaigns. You can see like an example of a subgraph from this data in the top right corner. So we can see the review. That review has an author, has a brand and a style of beer, like IPA, and also the taste score. So we trained the knowledge graph embedding models with library called AmpliGraph, which we will later use during hands-on session. And you can see that the actual embeddings are presented in the bottom on the right-hand side, and we were able to identify some interesting clusters of users, for example, loyal users or passive users or increasing or losing interest, and it organizes beer customers into segments. There's also engagement score that we developed and used here, so the cluster could be distinguished by this engagement score as well. So we finally reached the software ecosystem, and I can assure you that there are many libraries available for you to explore. On the top right, we can see like a short timeline we prepared in the first edition of this tutorial in 2020, and since that time all these libraries, like some of these libraries grow very much, some got discontinued and some new appeared, so and I will just refer you to the pointer, so if you want to explore them you can. So you have OpenKGE, C++ implementation, AmpliGraph with some nice features, PyTorch bgraph, we have DGL-KGE, we have PyKin, which grew very much in the recent years. We have PyKGE2Vec, have LibKGE, then we have GraphVite, MooKGE, which was just introduced this year, and Scikit-KGE, which discontinued. This is not an exhaustive list, but there are probably many more libraries. We just are not able to list all of them and use them all here, but this is just for reference. Maybe some library implemented something that you need, and you can just go straight to such library. For example, I don't know, if you need NodePiece, this was for example implemented by PyKin, but For example, if you have some problem with something, maybe you would like to choose AmpliGraph because it has active Slack channel. And to sum up, that's it. And your hands-on session with Showmeet will be happening next, and you will use AmpliGraph for this session. So thank you very much, and good luck. Here are some references so you can refer to the papers, and that's it from my side. Thank you.